Hey everyone! If you're an engineering student currently tackling numerical methods and trying to wrap your head around root location, well, you are definitely in the right place. Think of this explainer as your ultimate study guide to mastering simple fixed-point iteration. We're going to take this all the way from the abstract mathematical theory right down to the exact MATLAB code you're going to need for your lab assignments. It's going to be great, so let's just dive right in.
Okay, so here's the game plan. First, we'll compare open methods versus bracketing. Second, we'll break down the fixed-point formula itself. Third, we'll look at calculating relative error. Fourth, we'll visualize things using Cobb web plots. And finally, we'll write out that MATLAB algorithm.
All right, part 1, open methods versus bracketing.
So why do we even need new tools to find the roots of an equation? I mean, to answer that, we have to look at the tools you probably already know, right? Things like the bisection method. Those are what we call bracketing methods. Now, they're slow, but they are incredibly steady. As long as you give them an upper and a lower bound that actually trap the root, they will eventually find it. Open methods, though, they are a completely different beast. They only require a single starting value. But notice the massive trade-off we're making here. Because open methods aren't locked safely inside a bracket, they have the real potential to diverge. Basically, they can just fly off into infinity and completely miss the root. But, and this is a big but, when they do converge, they find that answer significantly faster than bracketing ever could. It's just your classic engineering trade-off, speed versus stability.
Moving right along to part 2, the fixed point formula.
Let's look at the actual core math that powers the specific open method we're focusing on today. And honestly, the foundation of simple fixed-point iteration is just a really clever algebraic trick. Usually, we're trying to find where a function equals 0, right? f of x equals 0. Well, instead of solving that directly, we just rearrange the equation to isolate an x entirely on the left-hand side. We can do this through normal algebra, or honestly, sometimes just by adding x to both sides of the equation. What we're left with is a brand new setup, x equals g of x.
And the absolute crucial point here is how this specific formulation creates an iterative loop. By treating the left side as our new estimate and plug in our old estimate into the right side, we get this fantastic predictive formula, x subscript I plus 1 equals g of x subscript I. It's like a machine. You make a guess, you plug it in, and out pops a better guess. Then you literally just take that new guess, plug it right back in, and repeat the whole cycle.
Which brings us to part 3, calculating relative error. But here's the million-dollar question. How do we actually know if our new guesses are getting any better? Because we're taking these leaps from one guess to the next, we need a way for our computer algorithm to track its own progress and, more importantly, know when to stop. We do this by calculating the absolute relative error at each step. You just take your new estimate, subtract the old estimate, divide that difference by the new estimate, and multiply by 100 to get a nice, clean percentage. When you go to write your while loop later, this exact formula is what tells your code to hit the brakes. As that error percentage drops, you know for sure you are zoning right in on the true root. Let's actually look at this in action with a quick example. Say we want to find the root of the function e to the negative x minus x equals 0. First step, we rearrange it to x equals e to the negative x. Now, if we start with an initial guess of 0, watch how the data behaves. After our very first iteration, our error is a massive 171.83%. Yikes, right? But watch what happens as we keep feeding the new value back into the formula. By iteration 10, our error has shrunk linearly all the way down to a brilliant 0.62%. Our estimate is narrowing in perfectly on the true root of about 0.567. This right here, this is linear convergence in action, and it's absolutely beautiful.
But what if things don't go so smoothly? Let's see how this can completely fall apart. You can actually rearrange that exact same initial equation into a different form. X equals the negative natural log of x. Let's start with a really solid guess this time, 0.5. Even with a good start, by iteration 1, our error is almost 28%. And by iteration 3, oh, the error has absolutely exploded to over 63%, and our guesses are just swinging wildly. This formulation is diverging. If you let this run in MATLAB without a failsafe, you'd literally be staring at an infinite loop right now as it moves rapidly, dangerously away from the true root.
All right, part 4, cobweb plots and visualizing convergence.
So why did the first equation work perfectly while the second one blew up in our faces? To really grasp this, we need to visualize it using what's called a two-curve graphical method. Remember our x equals g of x formula? Imagine splitting that into two totally separate functions to graph. y1 equals x, which is just a straight 45-degree diagonal line, and y2 equals g of x,
which is our curved line. The exact point where that curve intersects the straight diagonal line, that is our true root. When we iterate, geometrically what we're doing is taking an x value on the diagonal line, traveling vertically to hit the curve, then moving horizontally to hit the diagonal line again, and repeating. This constant back and forth bouncing literally draws what looks like a cobweb on the graph.
And the shape of that cobweb? It's dictated by one fundamental, unbreakable mathematical rule, the golden rule of convergence. The absolute value of the derivative of g of x must be less than 1. In plain English, if the slope of your curve near the root is shallow, meaning less than a 45-degree angle, your cobweb is going to spiral inward, and your errors will shrink. But if that slope is steep, greater than 1, your cobweb just bounces outward into infinity, and your errors grow.
This geometry brilliantly illustrates exactly what your iterations are going to look like. If the derivative of your curve is positive, you get a monotone pattern. Your steps approach the root from one side, kind of looking like a staircase. But if the derivative is negative, you get an oscillating pattern. Your guesses bounce back and forth across the root, changing signs with every single step, spiraling inward like a whirlpool. Both of these patterns can converge, but only if that slope is shallow enough.
And finally, part 5. Coding the MATLAB algorithm.
All right, we understand the theory, we've seen the geometry, we know the math. Let's get to the fun part, practical application. Here is the exact logical architecture you need to write your fixed point M file. First, your code needs to be robust. It should check that the user actually provided a function and a starting guess. It should also set some smart default stopping criteria, say a maximum of 50 iterations and an error threshold of 1 times 10 to the negative 6. Next, you fire up a while loop to run your iterations. Inside that loop, execute your core formula. Calculate your new estimate x1 by plugging the old estimate x0 into the function g. Then, calculate that absolute relative error we talked about. Now here's the important part. Instruct the loop to break if your error falls below your threshold or if you hit your maximum iteration limit. That second part is what saves your computer from crashing if your function diverges. If neither condition is met, simply set x0 to equal your new x1 and let the loop repeat.
When you code this up correctly and run our first convergent example, the e to the negative x function, this is the precise output your script is going to generate. The root equals 0.56714 with an approximate error of 7.67 times 10 to the negative 7% in exactly 35 iterations. Boom! It is a perfectly executed algorithmic search, doing exactly what our manual math did, just with flawless precision and blazing speed.
But, we can't let you off that easy. We are left with a pretty massive lingering issue. What happens when your only formula has a steep slope? Is there some modification of the fixed point iteration method that might provide a convergent scheme for a scenario where the standard method completely diverges? Well, that is the exact real-world challenge engineers face when dealing with highly unstable systems. And it's exactly what we're going to start unpacking in our next explainer as we look at advanced methods designed to tame those diverging functions. Until then, review that MATLAB code, try sketching out some cobweb plots, and always keep an eye on those slopes. Catch you next time.